because I know you've all taken physics already. What is acceleration? Simply put. Delta V over delta T. Delta V over delta T. Delta meaning change. Change in velocity over a change in a time period. And that will give us what we're going to call the average acceleration of anything. And that'll give us the average acceleration over a time period. Now, we take that idea, and right off the bat, we say if we want instantaneous acceleration, we're looking at dv dt. And dv dt is really equal to the derivative of velocity. Okay, so this is kind of where, if you remember last class, I think we ended off talking about acceleration as the second derivative. We never really got into it. It's the derivative of the velocity function. Or we could say, instead of the derivative of the velocity, we could say it's the second derivative of the position. And this is instantaneous acceleration. Very good. Instantaneous acceleration. So we've got average acceleration and instantaneous acceleration. Now, the interesting part you're going to notice about the way the AP course is run is, for the most part, things are looked at with a constant acceleration. And that actually helps me to figure out the term, because I don't really worry as much with the instantaneous. But we're going to see how this plays a role when we get to integration. When you start doing integration in calc, and we start looking at area under curves. So let's begin with an example for today. Yeah, let's start with an example right off the bat. So let's say we've got the following. First of all, what are the units for acceleration also? What are my units?
Meters per second squared.
Yeah, meters per second squared. Those are going to be my units, meters per second squared. The units also indicate to me that it's a second derivative because I see second squared. Velocity is the first derivative, and it's meters per second. When you take the derivative with respect to time, it adds on another unit of time in the denominator, always. So if I did the third derivative, which I talked about, I called it, remember I said it was jerk, was the name of it? The third derivative is meters per second cubed. The fourth derivative is meters per second to the fourth, etc., etc. Okay? So when you take derivatives with respect to time, you're constantly adding a second into the denominator of the units. If it's already there, it becomes second squared, etc. In general, something we should know, and I'm going to get into the first one, but I don't want to skip stuff altogether. In general, you should know that 1g is equivalent to 9.81 meters per second squared. And at times, you'll hear textbooks use terminology like 3Gs, 4Gs. An astronaut feels 5 Gs upon leaving the atmosphere. Gs are simply quantities of units of gravity on the Earth. So if I hear 3 Gs, it's triple 9.81. 4 Gs is quadruple 9.81. So G's, it's not a unit really, but it's a small value of acceleration. It's a discrete value of acceleration that you can use as a multiple of to get the other values in a sense. I feel like we're missing something today.
Jack. Rest in peace.
Is it just 10 or is it 11? What is it? That is 10. Okay, what's the other class? I thought it was 11 for a second. Oh, my mentor is 11. That's what it is. Okay, so a G is 9.81 meters per second squared. Again, signs matter. Signs matter. If I have, let's make a chart here. If I've got velocity and acceleration and motion, you'll remember from my course last year, if you haven't, that I made a point to emphasize this a lot. This is where multiple choice will play a role, even on an AP level exam. If I've got velocity and acceleration, and I look at their signs are enough to tell me about the motion. For example, if velocity is positive and acceleration is positive, what must be happening to the object? More than that? It's speeding up. It's speeding up. The fact that the velocity is positive already tells me that shit. The acceleration also being positive means that the velocity is increasing now, thus speeding up. It's speeding up. What if the velocity is negative and the acceleration is negative? It's still speeding up, but in a negative direction.
It's like subtracting something by negative.
Yes, it is very much like that. That's how you can remember speeding up. If the signs are the same, it's speeding up. Now, when the signs differ, it is slowing down. So positive velocity, negative acceleration, or vice versa, it is going to be slowing down. And I'll put as the last column here, if you want to put the direction it's moving in, if that helps. Since it was a positive velocity in the third case, with sometimes we call this a retarding acceleration, like a deceleration, something that slows down your motion. I know it sounds like the word retard. Retarding acceleration or retarding force. The viscous force of water, the resistance you feel when you run in Central Park, those are retarding forces because they're opposing your motion. So in both of the third and fourth cases, the acceleration is opposing your motion. That's why we're slowing down. Now, because our direction or our velocity was positive, this third row is like moving this way, but feeling it slow you down. So your direction of motion is still positive in the third case, even though you're slowing down. But in the fourth case, your velocity is negative, so you're moving negatively, but the acceleration is positive, so you're moving in the negative direction here, you're still slowing down. So those are our four scenarios that we could have between velocity and acceleration. Okay? What about when the acceleration is 0? What can we automatically assume or conclude? Velocity is either constant or 0, which is still constant. Yeah? Okay, whenever acceleration is 0, velocity cannot be changing. Whenever acceleration is 0, velocity cannot be changing.
What's an example of when velocity is negative and acceleration is positive?
Here?
Yeah.
Anything. You could be moving west, which is considered negative velocity, with the wind pushing you east. And it just means it's opposing, that's all. So this is only giving us the direction we're moving to start. These being opposites are just saying that the resistance we're feeling is opposing our motion. Where does acceleration come from? It comes from a force, right? After it was MA, we haven't gotten there yet, but we're going to get there. So when we think about acceleration, it's like an opposing force. Air resistance is the best example. Air resistance, 9 out of 10 times, opposes your motion. It's rare that air resistance helps your motion. That's when you have like headwinds versus tailwinds on planes. Okay? But for the most part, when you think of objects moving, air pushes against the object moving. Okay, for the most part. Obviously, there are days where the wind gusts, like it's at your back, and you're running, you feel almost like it's helping you. And then it would be positive, positive, or negative, negative. All right, let us look at an example. So simple example, AP exam you could expect are things like this. It'll say the following. A particle's position is given by. Okay? It'll say a particle's position is given by the following. And then it'll ask some follow-up questions. Okay, it'll ask some follow-up questions. The first question will say this. When is the particle at rest? When is the particle at rest? The second question will say, what is the velocity after 3 seconds elapse? I should really say at 3 seconds, not after. I'm going to write that as at instead. What is the velocity at 3 seconds? What is the speed at 2.1 seconds? Finally, what direction is the particle moving? And I'm spitballing these questions. This is not out of the text, this one. I'm just having to look at an example I have, trying to come up with other things that we could think of. Okay, so if we have a couple questions like this, right away, we look at this problem and recognize it's asking me about velocity and speed and being at rest. So I'm really caring about its motion, but the equation I'm given is not an equation of its motion, it's an equation of its position more. So what might I start a problem like this right off the bat? If I'm asked about velocity and I'm given a position function, what might I do right off the bat, Matt? Take the derivative right off the bat. Okay? So let's start with our work over here. So we have our question up at least now, right? Let's start with our work for this. So, what's our velocity function going to be for this? Chris? Yep, 4t plus 3. Now that you know the power rule, we don't have to use the limit derivative definition. You get it every time. So that's the velocity function. Do I need the acceleration function? Do I need the acceleration function? Based on my first 4 questions. Based on my first 4 questions, do I need the acceleration function?
Not necessarily.
The half answer, yes I know.
Well, I was thinking, because you could find the direction very easily with, if you have the acceleration. But,
Not necessarily. I can do a weak positive. Maybe it's acceleration.
It's not.
You don't need it yet. You do not need it yet. We're going to get to the point where we need acceleration as a function. Let's start first with this problem, the idea of velocity. But what is the acceleration in this case? Slope. And what's the slope of the velocity function, simply? Thank you. The constant drops off of the derivative, right? The derivative constant is always 0. So the acceleration function is 4. What does that mean about the acceleration? What can you already conclude about the acceleration, Max? The acceleration is a constant. The acceleration is not changing. The acceleration is not changing. Everybody see that? That's really useful because when acceleration is constant, remember the big 3 or the big 5 or whatever you called them last year, if you remember? X equals VOT equals 1 half AT squared, V squared equals VS squared plus 2AX, all that stuff. Those equations of motion only hold true for constant acceleration problems. So those equations of motion can be used in this problem if we wanted to, because it's a constant acceleration. And we're going to get into the fact, or the point, when it's not a constant acceleration, then what do we do? Then what might we do?
How do you know that it's constant? Sorry.
Because the acceleration, there's no t in the function now. I took another derivative, right? And the derivative of 4t plus 3 becomes 4. Yeah, look for the variable, the independent variable dropping off. All right, so the first question, part A, how would I go about that? How would I go about part A?
I said 0 equal to 14 plus 3.
Good, because we want to know when it's at rest. And when you're at rest, what's your velocity? It is 0. Very good. One person answering that. So 0 for part A. 0 equals 4t plus 3. And not a really reasonable answer because what kind of an answer am I getting? For now, for the time being, don't worry about it. It just simply means a couple seconds before we started for now. Okay, if it's on an AP exam, the function itself will most likely have something like this, right? It'd be like a minus here, so that this becomes a minus. If you want to do that actually and change these all to minuses, maybe that'll make it a little bit more reasonable later on, because your answer will indeed become, in this case, 3/4. And maybe make all those positives into negatives, so our question has a little bit more physical significance. Okay, so where you see I wrote red negative, maybe change all those to negatives, please. So after 3/4 of a second, so my answer for t again is 3/4. I should include units. 0.75 seconds. And this should be something that you're familiar at this point. Have you done first derivative test at Calc yet? I'm trying to think. Where you set the first derivative equal to 0 to find the max and mins? Kind of. You talked about the idea?
Like that specifically, or we know how to do it.
And you've already talked about position, velocity, acceleration in Calc, or have you got to that yet? Free fall problem. Okay, where you're given the S of t function and stuff?
So you haven't really done acceleration.
Got it. Okay. Good to know. Thank you. It's tough to keep me on pace. I got to keep track. All right. So part B would say what is the velocity after 3 seconds? So the velocity after 3 seconds simply v of 3, which is 4 times 3 minus 3, which gives me 9 meters per second. Again, I'm using my velocity function from up top, the first derivative. I'm evaluating the first derivative after 3 seconds have elapsed. So plugging the 3 here makes that 12, minus 3 gives me 9. So 9 meters per second. Is that my average velocity or my instantaneous velocity? Which one is that in this case?
Instantaneous.
Because why?
It's the slope of the tangent line.
Good, I like that, the slope of the tangent line. We use the derivative to find it. Anytime we use a derivative on the slope of the tangent line, we know that we're finding the instantaneous velocity at that moment. The moment is 3 seconds. So if I ask you for average velocity, can you do it if I only give you one time? Average velocity, what do you need? You need a starting time and an ending time. Okay, this is again at an instant in time, which is why this comes out to be the value it is. This is not your average velocity.
Is there a reason why you changed the negative?
Yeah, because I was saying earlier, if I left this positive, the first answer for time we got would have been a negative answer. And it would have been like, oh, your object's at rest, negative 0.75 seconds.
Oh, so you changed.
So I just changed the problem to make it work out. Yep. I made the function randomly just now, Tristan. That's why it came out that way. For part C, what is the speed at 2.1 seconds? What are your thoughts?
I took the absolute value of 4 times 2.1 minus 3.
Very good. So again, although this answer will definitely be positive because we know it already, if you just look at the magnitude of the numbers, we still want to write down absolute value. So if you're taking an AP exam and it asks you for speed and you simply put v of 2.1, they're going to mark you off even though it's the same answer. Is that clear what I'm saying right now? So make sure you indicate that when you're trying to find the speed at a given moment, you put absolute value around your velocity function. Even if it's the same number, which it is in this case, because this is 8.2 minus 8.4 minus the 3 gives us 5.4. So I know that the velocity is 5.4 and the speed is also 5.4, but my work should show absolute value around it. Again, that's more of a part 2 where you can lose credit for your work shown. A part 1 problem where it was multiple choice, you do the answer however you want to do the answer, right? You get the answer, you get it right, you choose. You do not need to, and your work will not be graded for any partial credit. Okay, so it doesn't make sense for multiple choice to do that. How about part D? What direction is the particle moving? This was a tougher one. Yeah, what are you thinking?
Positive.
Just positive?
Well, because the velocity is becoming more positive over time. So, it makes sense.
So I can walk this way with a very negative velocity and technically slow down, and therefore my velocity is becoming more positive. Then my velocity becomes 0, and then I can make my velocity become positive again.
The acceleration is also positive.
Think about it a little bit more.
Well, we have acceleration is 4, so we know we have to be accelerating in the positive direction.
We know that acceleration is acting in the positive direction, but that does not mean that we are moving in the positive. Remember, toss a baseball up in the air. Which way does acceleration act? Down. Yet the ball moves up for a while, doesn't it? So just because acceleration is positive is not enough information to say that we must be moving in a positive direction. It's not valid. It's not enough evidence shown. It's one thing that will tell us more about the snow.
Is your speed and velocity 2.1 seconds?
It's not those, but you're on the right track. It's going to definitely have to do with speed, velocity, something like that.
Like the y equals 0, x equals 175.
Well, this tells us when we're at rest, right? When we stop.
So then if you use the velocity, because that's the slope at that point, is that
What he's saying could help. This could help. Thinking about this, Chip.
Can you determine where the turning point is on the graph and sort of see what you get for each side
The turning point on what graph?
on the position graph?
That's one way to look at it. Everybody see what he's saying right now. If the position graph is increasing, it means your motion is to the right or up. And then if the position graph is decreasing, it means that your motion is either left or down. So we could plot the position function and find the max or the min to find the turning point. But that seems like a lot of work right now. And we have calculus in our mind, so.
Doesn't that mean it's going in two directions?
It will go in two directions for this problem, yeah. But we want to figure out, again, what direction is the particle moving? So we have to give detail. We can't just say both directions. It is moving left for this duration. It is moving right for this duration. Interval notation, like in calc. Interval notation. Next.
It's moving leftward from 0 to 3/4 seconds, and then it turns around and then it goes the other way.
Why?
Because that's when the velocity changes to negative velocity.
Yeah, how do you know that?
Because you said the first derivative of the equation equals 0.
But remember, first derivative equals 0 can give me a stagnation point.
Plug in.
Okay, did you do that though?
Yeah, if you plug in 0 seconds, you get -3.
So you see what Max is doing, remember? So again, this is where calc, I'm trying to keep track of where you're at. When you get the possible, what we call a critical point, right? In calc, you call this a critical point. You've used that phrase before, critical point? Okay. When you get a critical point, now the critical point can either be a max, if it's increasing on the left and decreasing on the right. It can be a min, but it could also be a saddle point in calc. You're going to learn about called a point of inflection, where the graph is increasing, flattens, and then continues to increase afterward. And that would be a different circumstance, and we'll talk about that. But in this case, Max already said, well, everything before this is negative, is going to move left, and everything after this is going to move right. And he said testing points. What does he mean by testing points? What does that mean exactly?
Plugging points on both sides
Plugging points on both sides
of the
of the critical value. So Max tried to number to the left of this in the velocity function, and then he tried to number to the right of this, and recognized he got a negative on the left, a positive on the right, which means that the position function is doing this really. Which means the object is moving left, stops, and then starts moving right. So although my position function looks kind of vertical, right? It's really dictating horizontal, linear, one-dimensional motion. So for a problem like this, the best way to think about which direction a particle is moving is just to analyze the velocity function. So you could have started by doing this, and just think about the graph of this. Think about the graph of this. Here's the graph. Right, that's it. 14 minus 3, your y-intercept is here. Your slope is 4, so I drew a positive slope. This is my velocity function right here I've drawn. And if I just look at my velocity function, I'll recognize that I'm starting with a negative velocity. Just as Max said, we're starting by moving left. So this particle moves left, slows down, and then hits 0.75 seconds. And when it hits 0.75, what's the velocity? 0. And then the particle gains positive velocity, gets faster. And it's getting faster because what kind of acceleration do we have? Positive acceleration. And the motion eventually becomes positive after, as Max said, the object turns around. So, when I look at my velocity graph, this indicates leftward motion. This indicates rightward motion. This is the stopping point right here. So when you see negative velocity, the object's got to be moving to the left, which is shown below the horizontal or t-axis. When you see positive velocity, it's got to be moving right. When velocity equals 0, it must be stationary. It must be stationary. So although we haven't gotten like crazy with like the physics type problems of this is a great problem you could expect next week on Friday's test. And the positive is that you're going to notice so much overlap in calc. So when you're studying for calc, you're kind of reinforcing what we're learning here and vice versa.
So could you maybe answer put it into notation like class T equal to like -infinity to
Let's do it right now. You want to use interval or set notation? Either one is fine. Interval is fine, yeah. So interval would be from 0. Actually, 0 is technically included. Yeah, because it has initial velocity as a negative. So including 0 up until 0.75, we could say it's moving left. Oh, actually not at 0.75 though.
It's at rest 0.75,
Yeah.
so it's not good for
That'll be a parentheses. I included 0, by the way, because this problem starts with some negative initial velocity. The problem starts that way. It's not starting from rest. So it's moving negatively during this time period, or it's moving leftward during that time period. And then yes, after that, it's moving rightward. Is it ever going to change again? For this problem? No. Okay? It's never going to change. It's never going to change. But at 0.75, it's not moving. Chip and that.
I was just gonna ask, like, get like a critical value of like 0.75 seconds. Could you do like negative v over 2 to get that?
Sure you could.
Or
Absolutely.
all the motion?
The axis of symmetry gives you the max or the min always. Absolutely, you can do that. But honestly, Chip, derivative is so much easier. You're going to need the derivative for parts B and C anyway, so why not use the velocity function just to get your answer? You follow what I'm saying?
Yeah.
But you could absolutely do that, and that's acceptable actually. It would be considered correct also. So you could find, he's saying, can you find the max or the min of the position function by using negative v over 2a? You can absolutely do that. And in this case, let's graph our position function so we can all see what Chip's talking about. Our position function would look something like this. Minus 2t. So y-intercept down here at negative 5, and it's going to be something like that. Okay? That's going to be our position function for this problem. That would be x versus t. And again, as Chip said, take a look right here. That's the maximum or the minimum in this case, where the velocity or the slope of the tangent is 0. So that's at 0.75 seconds right there also. Okay, so whether you do it this way or this way, it's the same. And as Chip noticed, going down is moving to the left, and then going up means moving to the right. And we've indicated our intervals the exact same way with either of the two answers.
So when it asks what direction the particle is moving, you want to graph the derivative and then where it crosses the x-axis is where it stops. And
You can do that, Matt. I'm not showing you that visually, but you could also do what Max said, which is called a number line test. Use this value, try numbers to the left, try numbers to the right. If you plug a number into the velocity function, take a look up here, plug a number into the left of this, like 0.5, that becomes a 2. 2 minus 3 is a negative quantity. So to the left of 0.75, you're going to have negative velocity just by testing a number in the velocity function. Then after 0.75 seconds, like after 1 second, try a 1 in here. That becomes 4 minus 3 is positive. So everything to the right of that will have positive velocity. So whether you graph it to visualize it, or you do a number line test where you test different regions on the number line, either way is acceptable. Okay?
And that's an acceptable way to like write the answer, right?
Here?
Yeah.
Yeah, absolutely. You should be versed in both though, because if it's multiple choice on a test, you have to know set. That's interval notation. Set notation would say this. Set notation would say 0 less than or equal to t less than 0.75. And then on the second part, it would say t greater than 0.75. Those would be your two answers for left and right. So this is interval notation. This is set notation. Okay? You should be comfortable from that, with that from your calculus course last year. If you're not sure about interval, it's really easy. By the way, because I'm saying this and assuming everybody is well versed in interval notation, interval becomes a bracket with an less than or equal to or greater than equal to. It becomes a parentheses with a greater than or less than symbol. Parentheses is always used with infinity. Anybody know logically why that is? Why that is?
It's not a real number.
You're on the right track. If you need more than that for the real explanation. Why is it parentheses here?
No endpoint. There's no endpoint, so you can't like cap it anywhere.
Good. I like that. It's not really an endpoint. You can't actually define that as a point or an endpoint itself. So you can't designate a region and assume it's included if you can't get to that endpoint. You'll never get to the quantity infinity, so it's considered parentheses always. Always. Okay? Good so far? All right. Very good. Let's go to 2.4, please. Let's go to section 2.4 now. 2.4, we're going to get into constant acceleration. I'm going to quickly run through the equations you need to know. So from the first equation we had a moment ago, we had this. We had average acceleration equals delta v over delta t. Now I can rewrite this as the following. v minus v0 over t minus t0. Where v0 and t0 are the initial time and initial velocity, and v and t are the current time and velocity. If you had me last year, I called that vf, or I called that tf, final. Same thing as current, meaning at the end of the problem. So this is my equation that I start with, and then it's sometimes very useful to assume that it starts a problem like this at time equals 0. So if we assume it starts at time equals 0, the equation reduces to this, which if you recall from last year, you can multiply both sides by t to get this. And then eventually this equation became the last line, which I'm going to show here. That's one of the big three we learned last year. Again, I hope you can see now, though, that the acceleration in this formula has to be a constant. Has to be a constant. We're assuming uniform acceleration right now. Okay, I'm putting the bar over for average, okay, but if it's average and constant, if it doesn't change and it's constant, the average and the constant are the same thing. Right? If I'm moving, think about it logically, if I'm moving with a constant velocity, well, what's my average velocity? It's the same value as the velocity I'm moving with. My velocity is 7 the whole time, then the average of 7 over an infinitely long time period is still 7. So sometimes you're going to see, I'm going to use that bar for that representation for constant. For all three of these equations, though, we should probably write a note that says acceleration is uniform or acceleration is constant. The second equation, that is very useful, comes from two other equations. So let's show that real quick. Can you, for Mr. Donachek students from last year, can you just tell me, did he derive the equations or just put them up? Where did you guys go about it? Because I didn't derive them for sake of time. He derived them for a while? I'll derive the first one and then talk about how you can derive the others, but I don't want to waste time just deriving things that you're not going to have to read around on the test anyway. So I'm going to show you it first, and then I'll say to you, like, you know what, the other equations you can practice deriving also. Okay? So the first equation that we're going to look at, or the first equation that we're going to start with to derive, let's start with our average velocity formula first. Okay, our average velocity equation. Now, we're going to again assume that t0 equals 0. And the reason we do that is a lot of the time problems you start them at 0 seconds anyway. So you don't need this t0 concept. So this equation then reduces a little bit further into this. We could then get rid of t by multiplying both sides by time. And we have this equation here, which we can really, if we want to, push ourselves and do a little bit more work. So what we can do actually next is we could take this concept of if you have a constant velocity, you also have the same average velocity. Remember that idea I just said? If I'm walking with 5 meters per second the whole time, my constant velocity is the same as my average velocity, which is still 5. So what we're going to do after this is say to ourselves, well, we can start with this formula. So keep this in mind. Call this, let's see. Your book does a number system. So I'm going to call this, let's call this equation 1 right here. Okay, I'm going to call this one at the top up here. Yeah.
For equation 1, would that be equal to v bar or just v?
No, just v. This is not the average velocity formula. This is the average velocity formula here. Okay? Yeah. This is the velocity at a given moment equals the initial velocity plus the average acceleration times time. Okay? So what we can do is this. We can start with equation 2. The book then calls the next one equation like 2a, 2b, 2c. So we can call this 2b, call this equation 2c for a moment. Because in a little I'm going to write down where we're substituting and how this is working. So with this idea of equation 2c, we're going to want to substitute into that equation in a moment. And to do that, what we can do is we could start with this idea, that if I wanted to find the average velocity in general, and I had the initial and the final velocity, I could simply take the average of those two things. Why am I able to write this? Why am I able to write that if I want average velocity, I can find the average of the ending and the beginning? Because some circumstances I cannot write what I'm writing here. Why can't I write this right now? What was that assumption you made earlier? Time is at zero helps, but that's not the assumption. Another one made.
There are 2 points given. Yeah.
That there are 2 points given, okay. There's another assumption we made. That acceleration is constant. Think about this for a moment, please. If acceleration is constant, what kind of a function must velocity be? Was it? Linear. Very good. Think about a velocity function like this. What's the slope of this function? Isn't the slope of a line a constant? So the slope of your velocity function would be a constant acceleration. So if we think about this logically, if I want to find the average, I can just use the end point and the beginning point and add up divided by 2. Because really I'm finding this secant there in a sense. So what I'm doing really is saying that I can use this formula because of constant acceleration. Now, what?
Is the change in acceleration based on the degree of the position?
The change in acceleration will affect our, what does acceleration affect? So if acceleration changes, you mean that dramatically? So if acceleration changes dramatically, then we have to start looking at derivatives and integrals of acceleration, of the dv/dt portion of this equation. So the assumption that it's constant just allows us to use these equations here. I don't know if that answers the question. You sure?
Yeah.
So what we can do though now is recognize that, look, we've got this formula right here, right? Take this expression and plug it in here. Take the expression from equation 1 and plug it in right there for v. So this becomes, oops. And I know this is lengthy, but stay with me. If I simplify this a little bit, I get the following. Oops. The V0 plus the V0 is 2V0. That's 2 of them. And then half of that goes back to 1. So I get an equation that looks kind of familiar, but it's not the right equation, or it's not an equation we're used to. The 1/2 AT, you should kind of recognize that form. It's squared usually, right? Yeah. You're like, oh, I see it, but I don't see it. Well, now you can take this guy right here, see it? And go back up to the one I said to hold off on, 2c, and plug it in right there. So remember when I said at 2c we like introduced this other equation here, and we came up with a new one, plug this back into equation 2c. So we're taking the first equation we derived, equation 1, v equals v0 plus at. We're using that in our average velocity equation, which yields this, and then placed back into equation 2c. And what will that yield? That will yield what's in blue I'm going to write here. That will yield the following. We're going to have v0 plus 1/2 at times t equals x minus x0. And now if we distribute, we see the equation develop that we're used to. If we start at the origin, this drops off. And then it becomes very familiar. X equals v0t plus 1/2 at squared. That's the common one you've always seen. If it doesn't start at the origin, we have an initial position to take into account. So the way that your AP exam writes this equation is as follows. It just moves over the x0 to the other side. Okay, that's the way your AP exam will use it. So the boxing ones are going to be the important ones that you're going to really want to remember, but you already know these equations. Okay, so the first one comes from the acceleration formula. The second one comes from a combination of what are like really three different formulas. Chip?
Just to simplify, can you write the equation out of the box, the blue one, as just delta x?
Yeah, you can absolutely write this as delta x right here. Yeah, because this is delta x right here by definition. Your equation sheet on the AP examiner writes it this way, so I'm just trying to be consistent, okay? So you're not like on the test, you're like, wait, this is new, what? Okay, but yeah, delta x is absolutely the same thing right there. All right, so that is your second equation.
Why do you remember the new equation under TC?
Because, if you recall, when we were here, Matt, we had nothing that we could substitute in for v bar.
Yeah.
So we had to introduce this equation that says, if it's constant acceleration, then the average velocity is the average of the endpoint, of the beginning point and the endpoint. And then once we knew that, we were able to plug in this v into here, which made this equation as follows, and then we simplified for average velocity, plugging it back in up there. Yeah, and again, the big assumption here is that acceleration is constant. It's constant, or uniform. Either word is fine. Okay? Let me jot down the last two. I'm not going to spend time going through them all, but let's jot them down so you can see them. So we have v squared equals v0 squared plus 2a delta x Now your book has two other equations that they do derive outside of these big three. Let me box that. Outside of these big three. But I don't see the use of them, so I don't know if it's worth going into them just yet. I'll write them down real quick, okay? I'm going to write them down, but I haven't found them to be useful. At least I don't remember even using them on when I was taking the AP exam. So the other two equations are as follows. Okay, this is one of them. And the other is make yourself a note. So those last two on the right are different than what you've seen. This is not initial velocity. That's why I don't really like this last one. It makes you think of this formula right here. The only difference is you see this negative sign right here? This becomes a negative sign. Instead of this being initial velocity, this is now your current velocity. So it could become useful, this formula, if you have a scenario where you're not given initial velocity, yet you have the current velocity. But you got to remember that this sign becomes actually a negative. And now, if you're working with vertical motion and gravity is already negative, then it becomes a negative negative, and it goes back to positive. So it can become a little bit cumbersome using those last two formulas. But keep them in the back of your mind. Anybody have the formula sheet handy on their notability? Did anyone save it yet for the year? Let's see real quick. Let's see if they even get these last two. Yeah, no, they don't get these last two. Okay, so I really would not use the last two personally, and your formula sheet writes this as x minus x0, right here. It writes this as x minus x0 on your formula sheet. So I should be consistent, sorry. Let's write it that way. Okay, let's write that as x minus x0 right here. Anyway, the other two formulas could become useful maybe in homework and problems, but they're not given on the AP exam, so I'm guessing that you either will not use them, or if you're really going to need it, they'll say something like, show where it comes from. These are combinations of other formulas themselves. So if you want to see, what was I reading through earlier? Where is it? Yeah, it's on page 24, okay, if you want to see where that comes from, on page 24. All right, what I'd like to do is actually jump into an actual problem. So we're in section 2.4 still. I'll wait until next class to get into free fall then. So I want to do an example of this. So the example your book poses is pretty interesting. It talks about what's called like the overcoming problem, where like one car is behind the other and they have to overcome them in a race. So you have like, they talk about the classic scenario. I've never heard this problem personally. But imagine if you had an airplane, a motorcycle, and a car all on a racetrack. And you say, go. Which is going to win the race? Which is such an open-ended problem that that's the whole problem itself. So if the race is pretty short, what do you suspect would win? Motorcycle. If the race is really, really long, what do you suspect would win? Plane. If the race is somewhere in between, probably car. You get what I'm saying here? Why is this? What's the rationale behind these answers we're all giving right now? Chip?
Because like there's a difference between like the acceleration that gives as a back end and maximum velocity.
Yeah. A motorcycle can accelerate real quickly, but the capacity or velocity is very low compared to an airplane, right? An airplane can get up to like 500 miles an hour easily, but a motorcycle is going to get up to like 100, 120. A car actually can get up to stronger than a motorcycle will, but it doesn't have the same acceleration as a motorcycle. So, and we're talking obviously like a race car. It's not like a Honda actually. We would not use in a racetrack. Just throwing that idea out there. So the problem is posed as the following. It says, let's assume for the sake of this problem that the car and the motorcycle are the only thing that we're interested in. Okay? And we're given in the beginning the following. Here's the information we're given. I'll dictate. Why don't you write down what's important this time? Okay, write down what's important from a verbal problem. Let's see if we can do it. So it says, here let's focus on the car and the motorcycle. The motorcycle first takes the lead because its acceleration is 8.4 meters per second squared. While the car's acceleration is only 5.6 meters per second squared. Again, the motorcycle first takes the lead because its acceleration is 8.4 meters per second squared, while the car's is only 5.6. But the motorcycle tops out at a speed of 58.8, while the car tops out at a speed of 106. Meters per second, I should say. Meters per second. So the question posed here is how long does it take the car, how long does the car take to reach the motorcycle and pass the motorcycle? How long does it take to reach the motorcycle and pass the motorcycle? Shoot.
What was the car's velocity?
The car's max velocity it could attain is 106 meters per second. The motorcycle is 58.8. So, talk to me first. We have to understand the beginning of this problem to go anywhere with it. What's happening? What can I physically say has to happen? And use physics terms, use terminology that you would normally say. And what are we looking for in this problem? We are looking for blank. And use some physics terms to fill in that blank. We are looking for the moment when blank. Yeah, but use physics terms. Remember? Yeah. So what would that mean? Very good. We are looking for the moment when their positions are equal. Well done, Chris. When their positions are equal. So we already know the fact that the position of the car and the position of the motorcycle will be equal to each other. So we can start by saying position of the car equals position of the motorcycle. That's our goal, to figure out when that happens. Now, the motorcycle can top out at 58, 58.8. 58.8. So, the motorcycle, how do we look at its motion? Because it tops out.
It would be like a curve and then tops out.
Nice. It's like a curve and then some sort of a linear function there. Because the velocity, the position is still going to increase, but once it reaches its peak velocity, the position is going to increase steadily from that point on. It's no longer going to increase like that. Remember, an accelerating body motion is this. Constant velocity position is this. Right? Position. So yes, we're going to have to break up the motorcycle into two parts.
They both start at rest, right?
Say again? They both start at rest. Yep. Okay, the goal is going to have to be breaking these into two parts, though. Into two parts. So, if I were to look at the car, since it starts at rest, I can write that its equation of motion would be what? If it starts at rest, use the last equations we had, and tell me what the equation of motion for the car becomes.
The equation of motion for the car becomes, in terms of,
Use the formulas in the previous slide.
so it'd be like the position would be x equals half 560 squared.
Good. Half AT squared. Very good. We're not using x0 because it started at the starting line. We're not using v0 because it started from rest. So even though this formula is really x0 plus v0t, do I need to include all of that? I don't. If you need to for now, that's fine. If it makes you comfortable by writing v0t and x0, give me a minute please, and doing stuff like this, that is absolutely fine. Now, for the motorcycle, we have two types of motion here, right? First, we have accelerated motion. And that's fine. But since it tops out at 58.8, eventually it's going to move with a constant velocity. So the second part of this is going to be the constant velocity of the motorcycle in part 2 times. Now, what is the t going to be in this case? How much time is it going to be moving at a constant velocity with respect to the entire problem? I'm not asking for a number, I'm asking for an idea. How do I figure out the time I'm going to use here?
How long it takes to accelerate?
Good. We have to take away whatever time this was that it took to accelerate up to 58. Because it's accelerating, say, for, I think it turns out to be like 7 seconds or something. But we know we have to take that away. So we can do this one of two ways. We can figure out what that time is, and then plug in t minus that number, and that's fine. We could also call that time something else, some other variable. And the time it takes to get up to that velocity is really important. So here I know that this is going to become t minus, and I'm going to call it t star. So I need to go back here and call this t star now. You see how I'm designating different times? It's very common in physics and in calculus to use an asterisk to indicate it's another time, but it's a little bit different, but it's not a new object. So I don't want to call this time 1 and time 2 for two different objects necessarily, so a star and asterisk is sometimes used. So this total time, minus the time it takes to accelerate, is how much time we're going to be moving at a constant rate, while this guy, the car, is accelerating the entire time. So we don't have to take away any t star from the car, because the car is always accelerating up until 120 or whatever it is. So for this kind of a problem, we need to approach it in this way. Give me one more minute. I know you guys got to go. That was the boat end of the day. The last thing we can do is, in the very beginning, if we recognize that this is, again, constant accelerated motion, we could figure out what this t becomes right here. We could figure out that actual quantity. Because what we know is that your, let's see, your velocity is going to equal your acceleration times time. And then this is, remember, plus v0. That's that equation from last slide. Well, v0 is 0 because it's not moving. So the time it takes while accelerating is really v over a for time. So this quantity can go in right there, and it can go in right there. So what I end up getting is this. So again, I'm simply plugging in stuff so I don't have to worry about numbers. The book initially said, oh, the time equals 7 seconds if you solve it. And that works. If you do, what was it, 58.8? If you do 58.8 divided by the acceleration of the motorcycle, you'll get around 7 seconds. But I'd rather plug in the variables v over a, so I've got a more powerful solution in the end. Now, if you look at this problem at this point, by the way, these A's are acceleration of the motorcycle here because we're looking at the motorcycle. We're looking at the motorcycle for this problem on the right side. So if I look at this, what's the only unknown at this point? T, time. So what we've done is we've created one giant equation of motion relating the fact that the car and the motorcycle will eventually meet up. And we're going to find out how much time it takes. So at this point it becomes what kind of solution? Good. Have your other numbers known? T squared and T are not known. This is a quadratic. You'll get two answers. Okay, now listen. The homework from this section, I'm going to send you an email tonight to give you a little bit of practice. That homework will obviously not be due tomorrow. You guys will leave for Kairos. But this is the homework that I want you to practice and work on when you get back from Kairos over the weekend. Okay, so we've done everything up to 2-4 in chapter 2. Okay, I'll try to send you more details about next week, outlining stuff, along with practical problem set questions. Okay, so please make sure you keep up with your work when you guys get back. Have a really good time on Kairos. It's a great experience. It's like any retreat. It's what you put in is what you get out. Seriously, whatever you put in is what you get out. Okay, so while you're there, keep that in the back of your mind.
Thank you. I'm
Cool?
sorry for this station.
It's okay.
I'm like planning to like
Sweet. Every time, yeah, come by.
Yeah.
Yeah, every time is useful. And that's for everybody, not just for everybody, yeah. Thanks, Tristan.
Thank you.
You're welcome, Max. For this class, it'll be multiple choice and then math answers. And in the math answers, they'll sometimes ask you to respond with like justifications. So why is the answer what it is? Why does it make sense? So you might give some verbal responses in the math part. But that's the way the AP exam is done, so I'm going to do it that way all year. Just so it's modeled the same way so you guys are ready for it.
And the test is going to be like the same level of difficulty as a homework.
You can expect, yeah. Like, I mean, I would say the harder of the homework problems is what you expect in the test.
Okay.
I don't usually like, if I'm giving you all level 2s on the homework, I think they did label 1, 2, 3 in this book, I probably won't choose like a level 3 in my mind for a test because you haven't had that.
Right.
But as the year progresses, I might start making it a little tougher as we go on. But I'm trying to kind of slowly get us in with the schedule or anything on.
Well, I'm sorry, I'm going. If we, when we say for the test, if I redo the homework stuff and the classwork, I should be fine. Usually.
I mean, I would definitely do that, but my recommendation would be to go right to the problem set also.
Okay.
So over the weekend, this weekend, you could do homework from 2-1, 2-2, 2-3, 2-4. But then, which I think you already looked at 2-1 and 2-2, right?
Yes.
But then next week, I would do the problem set as my assignment. I mean, we can still look back at the old questions for sure. And you know, if things like multiple choice, looking at multiple choice sample examples, I'm going to put up the multiple choice PowerPoint or whatever that was that I did for vectors for chapter 2 also. So those are good sample things to look at to get your mind thinking multiple choice ones.
Awesome.
Okay? All right, sir. See you later, guys. Nico, what's up?
Do you have any opportunity to like help me out?
Yeah, absolutely. You want to practice?
Yeah, I was just wondering, like, for the quiz tomorrow,